Hello and welcome to today's lesson on Newton's second and third laws. So Newton's second law is looking at forces and how they affect objects. As stated, it is the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. It's expressed by this equation that is F, or the sum of F, equals m times A, where F is net force, the sum of F is your net force. M stands for mass and A stands for acceleration. The sigma sign in front of the F is showing you that means sum of. So this little sign right here means sum of, or the total of all the forces, is equal to the mass of the object multiplied by that object's acceleration. And that is the equation used to represent this scientific law. And so what happens is, so if we have a force of 100 newtons, and if the object had a mass of 10 kilograms, it would also have an acceleration of 10 meters per second squared. Now, if this same force were exerted, 100 newtons, and we increased the mass, so an object this time had 20 kilograms, had a mass of 20 kilograms. So because we're talking inversely proportional here with the mass went up, which means your acceleration is going to go down. So we take 100 and divide it by 20. Your acceleration is going to be 5 meters per second squared. Likewise, if the mass were to go down, the acceleration would go up, and so on and so forth. We're going to look at this here in a second. You'll get to do some practice with it, but this is Newton's second law. So for example, Roberto and Laura, get my pen back. Roberto and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book toward Roberto. If the net force acting on the book is 1.6 newtons to the right, what is the book's acceleration? So we know that F equals m times A. And so I know that my force is, I'm looking for acceleration here. We're looking for book's acceleration. So to get, wow, that's a really bad line. Circle it, kind of. We get A by itself, we divide both sides by M. So I'm going to end up with A equals F over M. And we said that our force was 1.6 newtons. The mass was 2.2 kilograms. If you divide those two numbers, 1.6 divided by 2.2, you should come out with an answer of 0.73 meters per second squared, which is shown down here. So 0.73 meters per second squared to the right, because you divided those two, and that's what we got. This is Newton's second law. So pretty straightforward. Let's do the first one together. So a net force on the propeller of a 3.2 kilogram model airplane. So I know that I have a mass of 3.2 kilograms is 7 newtons. What is the acceleration of the plane? So again, we're doing F equals m times A. I'm solving for A. Oops, we're divided by M. So we end up with A equals F over M. We know that my force is 7.0 newtons. My mass is 3.2 kilograms. 7 newtons divided by 3.2 kilograms is 2.2 meters per second squared. It's worth noting, and I should have mentioned this on the last slide, that because F equals m times A, and the unit for force is newtons. So if I'm looking at units, newtons is equivalent to kilograms times meters per second squared. So we always have to be in kilograms for mass, and acceleration is going to be in meters per second squared. So this collective unit is the same as a newton. So instead of writing newtons, you could write this behind your force. So 7.0 kilogram meters per second squared. But the first one's 2.2 meters per second squared. If you want to do the next two, you can. I'm going to give you the answers here. But if you want to work through them and check yourself, you may do so. But your answers should be 27 kilograms and 14 newtons. So that's Newton's second law. His third law. The second law was looking at the acceleration of an object compared to the force, or as in respect to the force and the mass. This one, we're looking at two objects interacting. The magnitude of the force exerted by object 1 on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1. The simple version, the version that I always teach and that I remember, for every action, there is an equal and opposite reaction. For example, this guy over here is hitting a nail. So the hammer hits the nail with a force of 10 newtons. Because of Newton's, for every action, so the action is the hammer hits the nail with a force of 10 newtons. The reaction is going to be the nail hitting the hammer with a force of 10 newtons in the opposite direction. So equal and opposite, same value, same magnitude, opposite direction. And we'll look at this here. So we're not implying the net force is zero, just that the force is exerted backwards. So even though the action-reaction forces are equal and opposite, there still may be a net force at work here. For example, when you hit the nail with the hammer is going to exert a force on the nail that's got, say, let's call it 100 newtons. So the hammer is going to push on the nail with a force of 100 newtons. The nail is going to push back on the hammer with a force of 100 newtons. But this force can be greater than, so because of this, there's a net force going this way of 100 newtons. And it's going to hit a piece of wood. If the wood can only exert 10 newtons this way, the nail is still going to accelerate in this direction. And that is how objects can still move, even though equal and opposite forces say they have to be the same. So you can still have a net force even though forces are equal and opposite. For your action-reaction pairs, what you need to do to get them is you need to just flip the nouns. For example, my action force here is going to be, if I'm talking about the hammer and the nail, my action force is going to be the hammer hits the nail. The reaction force is going to be the nail hits the hammer. Those are your action-reaction pairs. It is not the hammer hits the nail and the nail goes into the board. You have to keep the same two nouns and you flip them around on opposite sides of the verb. Those are action-reaction forces. And that takes us to the end of today's lesson. Thank you for listening. And if you have any questions, please make sure you let me know.